Good evening, everyone. Good evening, Harry. Glad you're here. This is Mr. Batalha Soten, Evergreen Valley College. And the week of November 30th, that's this week, we are pretty much tackling one of the last chapters in that deals with the universe in large scale. We are pretty much focusing on our Milky Way galaxy. As we stud the universe in large scale, it is divided in superclusters of galaxies, and these superclusters of galaxies contain clusters of galaxies, and clusters can be poor or rich clusters, like Virgo. Our Milky Way galaxy, which is the subject of this week subject, is part of what we call the local group of galaxies. And our local group of galaxies include a few dozen of members, and Milky Way is just one of it. In this week, we have class notes, and I will go over some of this material. You do have homework and astro discussion, which is going to be the last astro discussion in the series. And then we have some questions, multiple choice questions. They are not graded, but they are there just for your enjoyment and to practice for final exam. So as we move on towards the last 2 or 3 weeks of class, we would like you to know there is major activities going on. Is the observatory this coming Friday. For those of you who haven't had the opportunity of going previously to the observatory or have not started the moon observation, that's your last chance to go to the observatory and enjoy the public viewing there and submit a report. Visit to the observatory amounts 10% of your course grade. And I haven't included that in your overall grade, but I intend to include it today or this week at the latest. Milky Way galaxy? Milky Way galaxy, yes. Milky Way galaxy, you mean? Andromeda. Or Andromeda? Oh, Milky Way and Andromeda galaxy? Oh, the discussion. Okay, I got it. You are blending them. Is that right? Plus Andromeda. Yes. Okay, got it. Yes. Well, Milky Way and Andromeda are the biggest members of our poor clusters of galaxies, and the other smaller galaxies happen to be clustering and being gravitationally bound to these two big galaxies. And one of the things we learn when we study the universe in large scale is that in a smaller scale, gravity controls the dynamics of the universe, which means in a small scale, the galaxies will tend to cluster and to group themselves into bigger members. So, one of the examples we learned in the previous chapter is that rich clusters of galaxies in general, they have in their very center of mass, in the central part of these rich clusters, they sometimes they harbor what is called giant elliptical galaxies. So these giant elliptical galaxies are thought to be the result of several mergers of smaller sized galaxies. and which indicate or which suggests that in a small scale, gravity is responsible for controlling the dynamics of the medium, and the galaxies just tend to merge, following the direction provided by gravitational force. So, in fact, Andromeda Galaxy and Milky Way Galaxy are in the route of collision. So, these two bigger galaxies in our local group of members, they are merging, they are colliding with one another. In fact, this collision will take place in another 3.5 billion years. And as they do, all these smaller sized galaxies, these dwarf galaxies that encircle them, will also be part of this future unique giant galaxy. So that's the idea. So in small scale, gravity takes over, but in large scale, in scale of superclusters of galaxies, space is the one controlling the dynamics. And what we observe is energy, which we call dark energy, is the one responsible for pulling apart all these superclusters of galaxies. And we call that the dark energy as being the element or the quantity or the parameter responsible for speeding up or accelerating the expansion of our universe. So let's take a tour over this week's slides. So if you happen to go to a very dark site, a site that doesn't have light pollution, assuming the moon is not in the sky, and you're not in a parking lot that has illumination, or you're not in the window of your house that has some internal illumination. If you look up to the sky, this is what you see, the Milky Way galaxies. Let me see if I can bring to your perspective um, what I'm trying to convey. Just a second. So the Milky Way galaxy is a complex structure of about 300 billion stars, and the stars, they all have their own star system, which means they come with planets and everything else. So let me show you this. So if you look outside right now, this is what you see. You see these stars, but can you see the Milky Way galaxy right here? So you have some fuzzy patch. Let me see if I can even make it bigger like this. See that? So if you look across here, I can speed up the time too. See if I can do that. So now is November 30th, 8:14, and I will speed up the time. See that? So here's this north, south. The moon's over here, right? And on the west should be in our right hand side. Wait a second, I'm putting a proper position. Okay, there you go. That's better. See the Milky Way right here? Let me stop the time, the flowing of time right here. So here's the Milky Way galaxy. In fact, all these stars that you're seeing in this picture, they belong to our Milky Way galaxy. And if you look across this direction, you're looking in the disk of our Milky Way galaxy. And those stars up here, they happen to be above the plane defined by the Milky Way galaxy. The Milky Way galaxy, according to the figure that I showed you previously, right here, is like a pancake, and we, let's see if I have a better picture here. So the Milky Way galaxy is a spiral galaxy, and we, our solar system, happen to be about 30,000 light years from the center of the Milky Way. So here's the Milky Way galaxy. We do have a bar-like structure like this. As you can see, the bulge is not exactly globular or like a sphere, but it's more like a bar-like structure out of which the galactic arms comes out. See that? So we have one arm, which is the Perseus arm. We have a Centaurus arm coming out of the opposite direction, and the Sun in the solar system happen to be part of the Orion's arm. And the distance from where the Sun is to the galactic center is about 30,000 years. So standing in the solar system and looking, imagine this is a big pancake, right? And the center, the galactic bulge, this bright part over here, is kind of expanded and goes above this pancake-like structure. And the Sun is just a blueberry inside that pancake, and we, as part of that blueberry, happen to be looking across the dough. And when we look across the dough, this is what we see. We see this patch, these dark lanes, which consist of dark and absorbing material, dust primarily, that absorbs the light of stars in the background, and then we see that quite amazingly described in this animation right here. See that? Now, if you look in one direction, you might see some of the galactic disk. But if you allow, in fact, let me take the daylight out of picture. Nighttime is gonna come. Let me see if I can take the daylight. I'm still getting used to the software. I would like to get rid of the daylight, but view, night vision, full screen. There you go, high daylight. So the Sun is over there, right? So you see, as this progresses, you see the Sun, stop there. You see the Sun next to another part of the Milky Way galaxy. See that? So this is the part, if you look towards the Sun, we see some extension of that pancake-like structure that I was mentioning. And it goes and curves around, and that comes the other part of this pancake. That's the Milky Way. As if you could look around in 360 degrees, and then in one direction looking towards the galactic center where Sagittarius constellation is, you can see some of the galactic arms, and if you turn around, if you could, you would see the other extension of that pancake-like structure. So Milky Way galaxy is one galaxy in the universe, and we happen to be living in it. Okay, our Sun happens to be part of it. Now, how can we probe this galaxy? Well, you can see it depending on the type of radiation or detector you have. If you look with your unaided eyes, basically that's what the Starry Night software, the picture that I show here, that's basically what you're gonna see, especially if you happen to be in a very dark environment without light pollution. You look up to the sky, and then you're gonna see these dark lanes and these whitish patches. which indicate a collection of stars that happen to belong to our Milky Way galaxy. And all these little dots you see here and there in the Starry Night software, they are, in fact, stars, members of our Milky Way galaxy. They just happen to be, as I mentioned, closer to us and above and below this pancake-like structure. So our Milky Way is a spiral galaxy. Here is this dark lanes indicates the presence of dust, and dust can only exist if the gas that allows for condensation to take place, in fact, for crystallization of dust to take place, if the gas has sufficiently low temperature. And if the gas has sufficiently low temperature, then star formation can take it over, and then it can be a regular process in that galaxy. So spiral galaxies like our Milky Way, they undergo star forming processes, and and um, and which indicates the gas having a low temperature level, and indicates also that stars are being formed, the stars are dying out, the gas is being naturally enriched by metals produced by stars as a result of stellar evolution, as we studied in previous chapter, and pretty much that is what it is. Now, our Milky Way galaxy, because it's a spiral galaxy, has several thousands of giant molecular clouds, and these giant molecular clouds are the sites of star formation. So they allow star formation to be processed. Now, because these giant molecular clouds are close, they produce enough dust, and thus produce what we call uh, reddening. So reddening is the shift, is the result of, for instance, you have a star that is in the background, and between you observer and the star, let's say a giant molecular cloud happen to be in between you observer and that star. So when you observe that star, you are going to see the star slightly redder than it really is. And this reddening is not an intrinsic process of the star, but is the result of the interstellar medium, depleting some of the blue radiation, the blue photons, this star particularly emits. I'll give an example. When you look towards um, the horizon in a sunset, you see the sun kind of a slightly red, right? Same thing with the moon. When the moon sets, a full moon sets um, early in the morning, you look towards the horizon and you see this kind of an orange color full moon. Why orange? Why redder? Well, the reason is the longer and wavelengths, which are redder, they have the ability of going through the dust, through the aerosols in the atmosphere with more efficiency than the blue photons, than the more energetic photons that tend to be scattered. So they don't pass through this thick gas with the aerosols. So what we see most efficiently is the redder and longer wavelengths, and that's why the sun, and the setting moon or setting full moon, they appears kind of a reddish or orange. And phenomena is even more prominent if next to the place where you're observing, it happened to have a burning fire or forest fire, because the amount of aerosols going to the atmosphere will increase and enhance this reddening process. So the main point here is to indicate the interstellar medium produce what we call reddening. and the wavelength tend to be slightly um, shifted towards the red. This is not redshift. This is not redshift. Redshift is the Doppler effect that is the result of certain stars moving away from us. And then when we detect their uh, transitions, the transitions appear to be slightly shifted towards the red. It's the result of Doppler effects, the result of a changing frequency as a result of the relative velocity or speed between the observer and the source of light. Reddening it occurs regardless if the star or the galaxy comes towards you or move away from you. It is a phenomenon that is caused by the presence of dust in the interstellar medium. So, spiral galaxies, a hallmark of spiral galaxy is the spiral arms. Why do we perceive, why when we take pictures of spiral galaxies, we do see spiral arms? So spiral arms, it seems, it looks like for somebody that first thinks about, it appears that spiral arms are regions that are more populated by stars than the region in between the spiral arms. So you look at spiral arms here and another spiral arm in there. In between, you see kind of a dark, and then you might think the regions between spiral arms have much less stars than the region in the spiral arms itself. So here's the thing. In the spiral arms itself, right in this kind of a brighter lane, what I mean, the gas in there is slightly denser, is densified, is compressed by what we call gravity waves. And these gravity waves in general are the result of interaction of galaxies with the neighboring galaxies. And as they interact, these gravity waves spread throughout the galaxy, and as it compresses gas, it initiates the process of star formation. So what I'm trying to say is the major difference between the spiral arms and the region in between spiral arms is that in the regions where the spiral arms are located, you might have some small percentage of OB association. And we studied before and we learned what O and B stars are. So O stars, what's the difference between O stars and B stars? Milky Way differential rotation causes spiral arms. Um, well, the differential rotation, um, in fact, the galaxy rotates, right? But there is something in the galaxy which is dark matter. So dark matter haven't been observed yet. I mean, there are candidates like WIMPs, which are exotic matter. Uh, when I mean, years ago, one of the candidates for dark matter, which now is not adopted anymore, was black hole, because dark matter it should be inputted in the galactic environment because we detect that stars that are further away from the galactic core, they tend to go around the galactic center at a speed that is much faster than predicted by Kepler's law alone. And the only way we can resolve their observations and explains the observations, which means at a certain distance, much further from the galactic center than where the solar system is located, the stars go around the center at much faster speed or orbital speed. And the only explanation we have to provide here is to assume that the galaxies all around is surrounded by some type of material which we don't know what it is, and we call dark matter. Okay, dark matter uh, explains why the spiral arms are the way they are, and they are not tightly wounded around the galactic center. I mean, the galaxy, since its formation at about 10 billion years ago, the solar system has gone through the galactic center more than 50 times. And if you wind it up the gas 50 times, you're gonna have like a roll of strings all tightly wounded around a core, around the bulge. So since we don't observe that, and since it was measured precisely, then the only explanation is dark matter. Okay. So let me see what you wrote there. Causes spiral, maybe more dark matter near center more. So the dark matter, the model to dark matter, the distribution of dark matter in the galaxy is not one that goes along the plane of the galaxy, but it's one that surrounded it all. It's all around the halo and the galactic center too. And the combined gravitational pull of this entire dark matter is what causes this different the orbital speed to be the way we observe. Right. So so Milky Way is a barred galaxy, and how do we know our galaxy the way it is? I mean, who was the first one who came with a distribution, with a certain landscape, uh, with a certain picture of what our galaxy really is? Well, the first one was Sharpley. So what he did, he was an astronomer observing globular clusters, and he found that globular cluster, which astronomers knew at that time, is a group of very old stars. In fact, they were formed at the time the galaxy itself was being formed. These globular clusters, they contain thousands, in fact hundreds of thousands of stars in it, which make them with a strong gravitational field. Right now, in our galaxy, stars are being formed, but the gravitational bound of these stars are not big enough to keep them together for a long time. And once the stars are formed, these associations that include a few hundred members, the gravity is not, as I mentioned, strong enough to keep them there, and the stars just disperse, they just go away. Our sun supposedly was a member of a association that now is a single star, right? All its members are gone. All these galactic, as we say, galactic clusters, all its siblings are gone. They became dispersed because the gravitational tide was not that high. In globular clusters, because the amount of stars are much larger, then gravity is efficiently keep them together. So globular clusters, detecting them, we are detecting kind of a relics of our solar system formation. And Harlow Shapley, what he observed was that in these globular clusters there was RR Lyra type of stars. And then he used uh, the relation between periodicity of this RR Lyra star, and their magnitude, their brightness, to establish distances. And what he did was pretty much coming up with a picture of our galaxy. What he found was globular clusters. So here's the sun, that's where he is. All these globular clusters, they seem to be all over the place, but they seem to be centralized around a region that is seen in the direction of Sagittarius. Okay, and that's what you see in this picture now coming out of Earth, if you will. And so Harlow Shapley was the first one who gave uh, in fact, who advanced the first explanation as to why the center of our galaxy was not the solar system. In fact, the center of the galaxy was somewhere in the region. If you look straight towards Sagittarius, the galactic center happened to be in that direction. And now we have improved observations, and we are about 30,000 light years from the center of our Milky Way galaxy. So, briefly speaking, the Milky Way galaxy has a dimension of about 100,000 light years, as you can see in this figure. It has some spiral arms. It has the galactic bulge, which is about 30, about 10 to 20,000 light years, the galactic bulge, and the whole galactic halo, where dark matter happen to be distributed, and as well as galactic globular clusters, the halo is somewhere around 300,000 light years. See if we have something there. So that's halo. So halo, the galactic halo, is comprised of old stars primarily. The stars that can be found there are grouped in globular clusters. You might find some gas as well, and dark matter. That's the major component of galactic halo. So the solar system is located in the disk, not in the bulge. So the star populations in the bulge are old stars primarily, right? The disk stars are younger stars. So star forming regions occurs in the disk, and you also have old members in there, but in general are second generation of stars, and the halo are also old stars. So where in the Milky Way is the solar system located? In the disk. So stars in our galaxy, in the universe in general, are primarily hydrogen and helium because that's how they started. But as stars evolved, and we studied this in previous chapter, they initiate production of metals, and when they die out, these metals they produce are partially distributed back to the interstellar medium. That's another profile of our Milky Way galaxy. The distance between the Sun and the galactic center is about 27 or 30,000 light years. The dimension of the galaxy altogether, spiral arms to the edge of the spiral arms, about 100,000 light years, and the thickness of this pancake is somewhere about 2,000, 1,000, 2,000 light years. That's how thick the galaxy is. The Sun is a second generation of stars because it has metal on it, and and that perhaps is the best or the key point of this chapter is to introduce dark matter as the unseen component, in fact, of our galaxy. So about 90% of the material in our galaxy required to explain the dynamics of it, 90% of it is dark matter, believe it or not. So we know Newton's law explains observations, explains that we can send with very good precision probes to objects in our solar system. So Newton's law works quite well. We see Newton's law working quite well in binary systems, and we can make good predictions, ephemeris, and everything. So if Newton's law works well, it should work well also in the large scale of our Milky Way galaxy. And it doesn't. I mean, in fact, what we observe is not explained by Newton's law, Newton's gravitational law, and the only way to get about that is um, by including an unseen type of matter in our galactic halo, and we call that dark matter. And here's the graphic that explains that. So, according to Kepler's law, this curve should falls and falls and falls and fall, but it doesn't. It keeps increasing. And to explain that, to create a model that explain this rotational curve, we must input dark matter in our galaxy. Now, we finished this chapter emphasizing that in the core of our galaxies, as well in the core of any major galaxy, it lies a black hole. In fact, a supermassive black hole is not just a black hole. In the case of our galaxies, they have a few million solar masses. So it's a quite of a black hole if you think. So this black hole is there because the way the galaxy itself was formed. When the galaxy was formed, gas was brought to the region where the galaxy is. And in the very central part, the concentration of gas was high enough to initiate star formation right there. And once the stars initiated their formation, they exploded and died. And high mass stars formed black holes. So once this black hole was first formed, it was just formed in an environment that was very much dense and rich in gas. And this gas start to accrete and fall onto this newly formed black hole. And and the more the gas falls, the more massive the black hole became, to the point that now, according to observations of stars going about this black hole, it should be somewhere around 4 million solar masses. Just think about it, 4 million solar masses. So, what is the evidence we have of such a hole? Well, there are several. First of all, to explain the families of all these young stars that happen to be seen in the galactic core, you must include the presence of a very concentrated and located mass of this value, 4 million solar mass, in such a small volume. Well, according to, again, gravitational Newton's law, in fact, with expansion to Einstein general theory of relativity, this mass cannot be lying around without clustering into a black hole, without following in itself, without stopping forces in the universe that can prevent the collapse. So eventually, all these 4 million solar mass, which is there, and we see the effect of it in the motion of these stars that you can see in this picture right here, right? All these dots represent position of stars that have been observed. So the only possible explanation is a black hole. The second one, the motion of the gas in the vicinity of this black hole, can quite quite well be explained if the source of gravitational field is a black hole. it doesn't have an extension. That's what I'm trying to say. And then what we found is galaxies in general, they all have their black hole. This black hole all undergo flickering and changes and quick changes in fluctuations in its in their brightness, and which again gives some upper limit to the size of the region producing this flickering. And again, the region is too small and the mass is too big, and the only entity we know in the universe that can convey and fit this description is a black hole. So pretty much this is the chapter on Milky Way. What happened with my Starry Night? Let me take it out. Any question, Hadi? All right, man. So congratulations on your grade on exam number 3. Got a great grade there. And we are approaching the end of this semester, so we have a couple of more weeks of lecture. So next week is cosmology, which is a fascinating subject. All right. Oh, they are good. Yes, yes, yes. Are you working on the questions given at the end of the chapter? Those that were old homeworks. Have you tried those ones? No. Those are multiple choice questions. The discussion questions are good too. Um, I think the most challenging one was um, why there is a paradox of two stars. Um, one is is red and the other is kind of a blue, and is a in a binary system. When they form, the more massive one is supposed to evolve. The Algol paradox, yes, they are supposed to evolve faster than the other one, and so it's a big paradox, that one. So the discussions are good. I have to get better and more material for the spring. Yes, the less massive appears to be evolving fast, which contradicts stellar evolution. Now, all of this change if you allow for exchanging material, right? That was good. If you allow for exchanging material between the systems, then the paradox is resolved. All right. Okay, so what's gonna be your major? Um, let me stop the, the taping now. Wait a second.